This class is related to estimation of confidence interval for model parameter. We already know how to estimate parameter, but this topic is going to discuss on the confidence interval of those parameter estimates. Let's see what we mean by this and how is it going to be important. So we will try to understand this taking some simple example. Of course, we're not going to take a ordinary differential equation here, just for better understanding and easier to perceive it. We are assuming that we are preparing some calibration curve between glucose and optical density, glucose concentration and optical density, right? So let's see, if I am having some experimental data, assume that we are having optical density measurement for glucose analysis is given in X, and corresponding concentration we know is for Y, and we will be using is a calibration. That means we will try to find out what is the slope and intercept. It is very straightforward, but we will be using it in mathematical perspective. Let's see what happens here. So it is actually easy to find out what is slope and intercept, but now we are taking something different. So if you have not taken, for example, in this case, if you have not taken this second reading, what would have happened? Is there anything wrong? Or maybe if I skip the fourth reading, for example, I have not taken the fourth reading, or maybe I have taken the fourth reading 2 times, I have not taken, for example, this reading at all. Is there anything wrong on that? Actually no, because when we are measuring or when you are taking those samples, though we are taking some 10 or 15 samples, it is fine, but those parameter values are actually, in ideal sense, they should not be dependent on your how many samples you are taking. But that is the idealistic view, that is the aim and C, that is intercept and slope. Ideally it is a constant, but it all depends on our estimation, because we don't know them, we have to find it out. So essentially, if we take more sample, if I don't take one sample, or if I take another sample, it is likely that our estimate value will change. It is our ability to find out what value we are going to measure, and there is no hard and fast rule how many samples you need to take for this calibration. Let's see how the picture change. But as I told you, if I am taking a different number of samples, or if I take one sample twice, our parameter value will be changing in each case. It is normal, but this kind of sampling procedure is repeated multiple times, and for each data set we are going to estimate the parameter. So essentially we are taking all those things as our starting point, but we will evaluate those scenarios. Scenario means, for example, I'm not taking at all this one first sample, I'm taking 2 times this fourth sample maybe, or like that. So different scenario, and for each case we are going to find out what are the parameter values are there. So let's see the example in the next slide. So for example, this is the original one, X versus Y, and we will be showing you here what is the slope, what is the intercept, what is the R-square value. So assume in original case I am getting 19.36 is the slope, 0.43 is the intercept, and R-square is 0.99. Now we are talking this approach when I am taking some sample with replacement. That means I will take out of whole box, I will take same number of, for example, here I am having 1 2 3 4 5 6 7 8 9 sample is there. So from this whole box I want to take 9, maybe some sample I will take 2 times randomly. So that approach of sampling is called bootstrap sampling. Let's see this case what is happening here. It is happening that, okay, for example, in this sample, same number of sample, of course, this 0.377 is missing, rather 0.48 and 10, this particular sample came twice, for example. And if we have this sample, our, of course, aim and C value will little bit change, not much, but some changes is there. Similarly, I can have another random sample, for example, this 0.16 is not at all there, rather 0.09 versus 2 is coming 2 times. And for this also I am having slope and intercept, this one. Or another distinct case we can also take, where I am having this 0.26 twice, but 0.09 is completely missing. So this way we can have a large number of sample we can actually create, maybe Manually you will not do it because you are having some bootstrapping function. We will try to utilize them, and essentially uh, this process will be repeated multiple times, and then you will see for each parameter I will have a large number of values, of course very similar, but it looks something a distribution kind of things. For m, c or r square we will have it. So we will repeating this process a large number of set, and then from those m values I'm trying to predict what is the confidence level. That means I want to say a distribution, you're going to get it from there, and that will be actually our objective in bootstrapping, to estimate the confidence interval. We can do it for a large number of things, and we'll find out the confidence interval of these parameters. Let's see one MATLAB example rather, which is more common for us. So maybe I will not take this one. I'll just close it, and I'll switch over to a MATLAB file which we are normally doing here. So this is one file that is also doing the same job. You can see our main function boot ci interval close, clear, format, all those things. Anyway, we are keeping it intact. Our x data is this one and our y data is this one. So first of all I will show you how we are going to get the fitness, or I will say the intercept and the slope for x and y model. So this is actually shown here. That is actually a function we created where I will take the x value and y value. So it is actually linear regression. It is straightforward. So x equal to, I will put one value length. So in the x I will add one values of 1. Then if I say b equal to x by y, means it will give you the intercept and slope. A very straightforward approach is there. And then I am calculating what is the model value. That means I already have x, and then I am multiplying with b. So essentially we can have the model y values, what is x and the slope. And then I am calculating r square values, which is a sum of experimental minus model square and experimental minus mean of experimental square 1 minus, and c and m are the intercept and slope values, and those things being calculated and it is being returned in the function out, frend function. So you can see here now at this point I will just run it and I will see what is happening. So you see we already know this is the first time estimate, that is the original one. So I can have m is 19.358. Actually you can see it in output window as well. I'll just show you the output window. You see this is the slope, this is the intercept, and this is the r square. It was the output from this case. And now I'll show you how to make the bootstrapping. Bootstrapping is really simple enough. Here the syntax is boot ci, that is confidence interval from boot sampling. 5000 is the number of boot sample you are going to do, and your model is the function which will actually calculate what you want to make for bootstrapping. For example, it will calculate the m, c, r square with x data and y data. X data and y data is the input to the boot ci, the original x and original y. And when we are passing it to your model, so every time what will happen, from the original x and y data it will transfer some values of x and y with uh, replacement values of original one. So this x and y will actually change every time with new x and y components. And finally all those values will be stored in bootstat for example 5000 times. So every time it will add up in the bootstat. And confidence interval also can be calculated. You can do it manually as well, nothing wrong on that. Now you see alpha 0.1 I am putting so that we can have the significance level for our estimate, and it is a percentile based method we are going to do. And let's see what is going to happen if I am showing only one time. I'll show you. You see, I'm putting a break and I'm just continuing. You see, now I'm getting x value of the same one, what original one, and y the original one. And first time it is original, but second time if you see, probably you will see it is and y values maybe same randomly we are doing. So I'm just checking, we'll have sometime new values. Probably you see this is new values because you see 6 is being repeated 3 times. You can see the y values are actually replacement. So 6, 14, 7, again 6. Similarly, corresponding x value you see 0.26, 0.26 and 0.26. That means some values has been deleted and some value has been repeated. So this is the input, and every time they are calculating the AMC and R square values. So this process will be repeated 1000 times, or for example here 5000 times. And then I'm just stopping it because we cannot continue it all the 5000 times for this case, and we are completing. So okay, now 5000 time calculation has been done. So this bootstrap is, you can see it is a 5000 into 3. That means for every time for these 3 parameters, that is slope, intercept and R square, 5000 times this data is stored in bootstrap. And CIL is the confidence interval percentile basis. You can see the lower limit of our percentile is 18 and 0.34, higher is 20.19. Similarly for intercept, lower limit is for example 0.06 and it can go up to 0.99, and R square value from 0.98 to 0.99. So this is the confidence level. Better I will show you the distribution of those values also using a histogram plot from this 5000 data set, and you can see this is very nice plot to see. So this is for slope. If I am doing it 5000 times, you see it is actually some kind of a normal distribution. So our mean, what we normal estimate, will be around 18 point or 19 point something, and this is the boundary of 5000 times if I am repeating. Similarly, this is the value for slope, somehow a normal distribution, and this is the R square values which is varying from 0.98 and 1 to some extent. This distribution is also a normal one. In mid value is somewhere 0.99. So from 5000 times histogram of this one, you can see a normal distribution can be achieved, and we are trying to find out what is the 95% confidence we will have the distribution. So we are actually going to get finally, I'll show you the final values. So confidence interval from 18 to 20 and estimate value is 19. That means this is our parameter estimate, and this is its confidence lower limit and upper limit. That means we can be 95%, for example here 90% sure that the intercept will be within 18.34 to 20.19, sorry, slope, and similarly intercept will be within 0.06 to 0.99. This distribution is really big one, and R square value is essentially from 0.98 to 0.998. so this is the confidence for our all estimates values. Hopefully you understood this case, and we can do the same aspect, same process for maybe in biological system model also for parameter estimations.